Greetings and welcome to online lecture series of HVAC and R. Uh, Now we start the third unit, that is the practical aspects of vapor compression system. And this is the first lecture on unit number 3 on refrigerant piping. Refrigerant piping pipes are generally transport refrigerant through compressors, condensers, expansion valves, and evaporators to provide the required refrigerant effect. So the line joining evaporator to compressor, this is generally a low pressure line. It is called as a suction line. The line joining compressor to condenser is a high pressure and high temperature line. So this is called as a discharge line. Line joining condenser to expansion valve, that is called as a liquid line, is comparatively high pressure, but it is a liquid line. So the temperature is comparatively less. And there is no such piping between expansion valve and evaporator. Maybe in theoretical cycle, this line is shown, but there is no piping between expansion valve and evaporator. It is expansion valve is connected just at the inlet of the evaporator. Suction line is generally insulated to avoid the heat in to the heat in intake to the suction line, because excessive superheating is not desirable. It leads to increase the compressor work. So to prevent the excessive superheating, generally the suction line is insulated. So wherever you found, especially for large installations, wherever you found the suction line insulated line in the refrigeration piping, that is obviously a suction line. Discharge line is generally color coded with a red color, and it is the hottest line of the system. And in between discharge line, there are some uh, uh, oil separator is also placed. So the pressure in the system is maximum here. Liquid line, the pressure is similar to the discharge line, but it handles the liquid. And a slight pressure drop happens in the condenser, but not that much difference between the pressure at discharge line and pressure at liquid line. So as far as the piping is concerned, for halocarbon refrigerant, copper piping is recommended. Ammonia, because ammonia attacks on copper. So in case of ammonia, generally steel piping is used. There are three types of copper piping generally used. K type is generally for the heavy duty, where the pressure range is high. M type is a lightweight, and L type is standard copper piping. So mostly L type for the most of the applications, L type piping is used. Copper tubing installed in the refrigeration system should be entirely free of dirt, scale, and oxidize. So initially, the open ends of the clean new tubes should be capped to keep contaminants out. So such type of during transportation of the copper tubes, so the sealed copper tubes are used, so that any dirt particles should not, or scale oxides should not enter, because during the if the air is present there inside air or some dirt particles, it creates oxidation reaction during the brazing process. So the care is taken for the copper piping. So this is about the brief introduction of refrigerant piping. In the selection of pipe size and material of the pipe, the following point must be considered. Refrigerant, brine, or any other fluid to be carried through the pipe should not react the pipe material. The pipe size should be so small that it should not create excessive frictional losses, and also the objectionable noise because of high velocity. It must withstand the pressure of the fluid. This care is taken while selecting the piping for discharge line. The cost of the pipe should be minimum, or maybe it is a last preference. It should not be compromised with the quality. So as far as possible, the minimum piping is recommended for minimum refrigerant quantity. So the cost factor is considered, but not the in as a prime factor. Then the piping requirement, if you see, the proper designing of refrigerant piping must be there. So for a smooth operation of refrigeration system, so it must satisfy the following requirement: the transportation of the amount of refrigerant to the evaporator to compressor, uh, condenser, and expansion devices. So proper circulation with adequate velocity should be there. It should provide the optimum pressure drop in the refrigeration lines. So excess, in order to avoid the excessive pressure loss, some bends and the excessive length is not provided. So pressure drop should be optimum, because the pressure drop, it causes uh, considerable effect on the performance as well as the COP of the system. Uh, uh, it should ensure the adequate velocity to return the oil to the compressor at all steps of unloading of the compressor to maintain an adequate level for proper lubrication. Because generally the system is working for different capacities, and depending upon the capacities, the refrigerant flow rate varies. So the adequate velocity should be maintained even for the low capacity to return the oil to the uh, to the compressor, because compressor should not be there should not be any shortage of oil in the compressor to increase the life of the compressor. So that care is to be taken. Generally, where the oil is, if the separator is not installed, in that case, the adequate velocity is must. Flashing of liquid refrigerant must not occur before the expansion valve. So there is some possibility that liquid line, there is some heat addition takes place after cooling also, subcooling also. And due to heat addition, some liquid refrigerant, even at high pressure, if it is exposed to some ambient, that liquid line of 40 degrees Celsius, 45 degrees Celsius, then there is a possibility of heat gain. And due to that, some refrigerant gets evaporated. And before flashing, if it happens, before expansion, if it happens, it may reduces the mass flow rate through expansion valve. So as far as possible, the flashing of liquid refrigerant must not occur before the expansion. Is not at all desirable. The care is taken that liquid line should not be exposed to the high solar radiation or any for any heat sources. Uh, the excessive noise should be avoided. That generally happens if the velocity is too high, then it creates a noise. Ensure that oil and refrigerant should not trap in between the pipe. So adequate velocity everywhere should be maintained. There should not be any trapping of oil or refrigerant, because if the oil deposits on the refrigerant piping, uh, already oil quantity reduces. At the same time, it prevents the rate of heat transfer as well, especially in the evaporator side and condenser side. It should prevent the liquid refrigerant from entering the compressor during the operation and idle time, because it is not at all desirable that liquid should enter into the compressor, because if the liquid enters into the compressor, it causes a sludging, so sticking of the walls, and may damages the walls as well as the compressor. So liquid entering into the compressor should be avoided. So the piping should be, especially the care is taken while designing the or layout of the suction line. It should maintain dry and clean system, so there should not be any leakage takes place, especially at the surface. So all the surfaces should be dry and clean, because even some dust accumulation will prevent the rate of heat transfer. So these are the considerations. These are the requirements for a good design of piping. There are seven. These are the design requirements. General piping requirements, it is recommended to have, if there is no stringent requirements, then type L copper piping tubing is recommended. Copper to copper joints, pickup 6 without flux, that particular it is used for the brazing operation. Copper to steel joints, the non-acid BAG28 non-acid flux are used. Then a properly supporting piping to account for expansion and vibration of the weight. So proper support should be given to the piping, and also there is a proper this such type of clamping should be there to account for the expansion of the piping as well due to heating. Then avoid installing piping underground. Underground piping is not recommended for refrigeration applications. So it's very difficult to recognize the leak. In case of leak, we need to dig it out. Not recommended that all the not recommended underground piping. That is the reason. Then the test entire refrigerant circuit for leaks. So before charging, it is very much essential that entire circuit should be leak-proof. Uh, because if the leak is present, the refrigerant, it is a costly affair, because even if the leak is available there, then if we charge the refrigerant, after a few days, refrigerant, the entire system will be vacant. So to avoid that, so leak-proof, the system should be leak-proof with the nitrogen gas. This is a typical refrigerant piping. We can say this is we start with the compressor. Compressor, there is a discharge line. The discharge line, this is the line provided for the hot gas defrosting. So hot gas bypass valve is, if it operates, then that hot gas is made to flow through the evaporator. So this particular valve uh, open generally for defrosting operation. At the same time, the additional provision is there for unloading of the compressor. So if the capacity is less, then through this pilot line, the discharge fluid is partially flows through the compressor. Okay. So not entire hot gas is made to flow through the condenser. So the capacity, that is a cylinder bypass, we can say. So the suction line is connected again to the discharge line. So this type of this is a discharge point. This is suction line. So the suction gas, sorry, discharge gas, high pressure gas is again made to flow through the suction line to minimize the compressor work, as well as to reduce the capacity sometimes. So the oil return provision is there. So yeah, this is the oil return provision. So through this, the oil return to the compressor. This is a condenser. This is liquid line. Then solenoid operated valve. These two expansion valves are used. Is the parallel pipeline is there through the evaporator to avoid the pressure drop. The suction line, so that is to avoid the entry of liquid to the compressor. So the suction line riser is used here. This is a riser, so it traps the liquid refrigerant here, and it doesn't allow any liquid refrigerant entering into the compressor. So this is a typical refrigerant piping. So at the same time, a typical piping where we can show how the oil is written. So the separate oil separator is provided here. So the refrigerant from the compressor, high pressure refrigerant, is entering into the oil separator first. In the oil separator, oil is deposited at the bottom, and from the bottom it is oil back to the compressor. So only vapor it allows to the baffles. Baffle doesn't allow the oil particle entering into the system. So if the oil separator is there, so no worrying of. So maximum oil is trapped in the oil separator, and only the gas it enters into the condenser. So it condenses. So again, the riser is provided. So whatever maybe the oil it remains, it again fall back to the oil separator, and through riser, then it is condenser, the condensation taking place. So then a receiver dryer is used before condensation, because this dryer generally trap some foreign particles and some moisture before entering into the expansion valve. So this is thermostatic expansion valve, then entering into the evaporator where it takes load of the refrigeration. And this is the suction line. Is generally the pressure range is low. If there's still some oil remains, that oil it comes in the casing, and it is deposited or collected in the sump. So this is the typical layout way. So first diagram, that is without oil separator. So here the oil separator is used. So with the help of this oil separator, uh, we can trap the maximum amount of oil in the compressor. So these are the typical refrigerant piping layouts. So generally, if you see the distribution of the refrigerant in the entire system, the maximum amount of refrigerant is present in the condenser, followed by liquid line, followed by evaporator. Because evaporator, it is in gaseous state, that's why the quantity of refrigerant volume is more, but the quantity is less. Then suction line, this is compressor, the discharge line, the high pressure line. So the mass quantity is comparatively less. So the maximum amount of refrigerant is present in the condenser, so adequate to minimize the refrigerant charge. The optimization of liquid line, evaporator, and condenser is required. so that the quantity should be as low as possible, or the adequate quantity is charged. Yes. And then the sizing of the copper tubing. Copper tubing is generally sized with the help of pressure drop equation. Refrigerant piping is designed mainly on the basis of practical line sizes without excessive pressure drops. So pressure losses without a change of phase can be calculated using a Darcy-Weisbach equation. So in the lines, generally it is already decided that what should be the minimum maximum allowable pressure drop. So based on that, we can use the Darcy-Weisbach equation. So this Darcy-Weisbach equation is only applicable for single phase fluid. So wherever there is a single phase fluid, except evaporator and condenser side, everywhere there is a single phase. So where delta P is the pressure drop, rho is the density, then L is the length of the pipe, D is the diameter, C is the velocity, F is the friction factor. For friction factor F in the suction and discharge lines, a value of friction factor is taken as 0.03, may be taken. Actually, this is F dash 4F. So point not something is generally a friction coefficient. So this is a coefficient 0.03 may be taken, whereas liquid line it is taken as 0.004. And during the sizing of a refrigerant piping, the system refrigeration load is known. So generally system is refrigeration load is known to us. So instead of velocity we can put in terms of mass flow rate. So instead of C, we can put m dot R upon rho A. So uh, delta P that is equal to rho, it goes this side. So rho FL, instead of C, we can put m dot R by rho A. So m dot R by rho A square and 2GD as it is. If you simplify this equation, that is FL m dot R square. So rho get cancelled, one rho still remains. And area, this is a cross-sectional area, pi by 4 d square. And instead of m dot r, we can put ql dot by delta h. So from this, we can develop equation of d. So if you take a constant, so d, the diameter of the copper tubing is generally a function of friction factor, the length of the pipe, cooling capacity of the system, then the enthalpy difference, that is refrigerating effect, and density of the fluid, and the pressure drop. So all these quantities generally known to us. So with the help of this, we can calculate the diameter. Once we get the diameter from the chart, also we get the velocity. These are the lines of various diameters. So we know the diameter, we know the capacity. So we can locate the point on the chart and get the adequate velocity. So this is the velocity we can calculate this way. So this way we can, during the sizing of the uh, piping, so first size with the help of allowable pressure drop, and then with the help of that diameter and capacity, we can calculate what is the velocity. And from the table again, we can cross check whether this is a permissible velocity or not. So there is a proper process of sizing for piping of any refrigeration system. So this is a typical refrigeration system, which is there are different lines we can recognize. This is a suction line, we can say. This is a discharge line, connect compressor to the condenser, then condenser to the evaporator, that is the generally liquid line. So these are the lining. Main, there are three types of linings. So first step, that is to determine the total length of the piping. So generally, while designing the piping, the individual line is designed. So for example, suction line, discharge line, and liquid line. So first of all, while designing a suction line, first of all determine the total length of the piping, then calculate the refrigerant velocity at maximum and minimum velocities, maximum and minimum capacities, so based on the diameter. Then they select the largest diameter that results in acceptable velocity at both maximum and minimum capacities. So it is very much essential that you should calculate the velocity for maximum loading as well as minimum loading. So QL dot, that expression we have seen, that diameter is a function of cooling capacity, and velocity is a function of diameter. So based on that, for cooling capacity, what is the lowest possible cooling capacity? First of all, we will determine. From that lowest capacity, we determine the diameter. For highest capacity, we determine the diameter, and corresponding velocity also we can determine. Then the total equivalent length of the straight pipe and fittings. So there is a table available. So for various pipe fittings, the equivalent diameter is given. So accordingly, the total equivalent length is determined for various fittings. Then for entire that equivalent length, the pressure drop due to pipe fitting is calculated, and check whether it is allowable, and add pressure drop due to accessories. Suppose accessories like this is accumulator case, some dryers are used, some receivers are used in between, oil filters are used. So pressure drop of these devices are already given in the table. So add that pressure drop and calculate the total pressure drop. So this way, pressure drops are calculated, and from the table also, what are the recommended values? Check that pressure drop, whether it is allowable pressure drop or whether it is less than the maximum allowable pressure drop or not. So accordingly, the design is validated. So this way, the process of sizing takes place. There are 6 steps of sizing the refrigerant piping. Then the suction line is the most critical line, because suction lines are the most critical from the viewpoint of design and constructions, because it must ensure the adequate velocity to return the oil to the compressor. That is the main rule. And the secondly, it should not allow any liquid particles entering into the compressor. So the considerations involved are of the following. So the correct size for practical pressure drop. So pressure drop should be as low as possible, because it is connected to the sun. But that pressure drop leads to increase the compressor work, which is not desirable. So correct size for practical pressure drop is recommended. So the line must be capable to return oil to the compressor by entrainment of the suction vapor under minimum loading conditions, especially in the case of fluorocarbons. So for high capacity, the question, most of the time that suction vapor entrain the oil to the compressor, but especially for the low capacity, there is a problem. So even for the low capacity or the minimum capacity, the adequate velocity should be maintained, so that whatever the oil particles present here or that is coming out from the evaporator, it should enter into the compressor. So that care is taken. So the line must be capable of returning the oil to the compressor. If there are suction risers, the gas velocities to ensure oil uh, have to be increased, because the suction riser is generally provided to prevent the liquid particles entering into the compressor, but at the same time, it must ensure that the oil should, whatever the riser height is there, that height should be sufficient, so that the oil droplet may carry over with the suction vapor. So that care is to be taken. Sometime in the low velocities or low capacities, there is a possibility of oil accumulation here. And if the oil, if the entire trap is filled with the oil, then it may block the refrigerant entering into the compressor. So there is a blockage of flow here takes place. To avoid that, that things second, that is double risers are used. A double suction riser is constructed of a large diameter riser with a trap at the base and a small diameter riser in parallel. At maximum capacities, the refrigerant vapor flows up both risers at velocities that are adequate to carry the oil droplets. So maximum velocity, there is no problem, because the oil velocity through both risers is sufficient to carry the oil droplets. But at the minimum capacity, the refrigerant velocity in two risers become too low to carry the oil droplets, and the oil from both risers therefore drains down. So there is not possibility of oil rises into the tube, so it drains down and it is collected in the oil trap. Uh, when this trap becomes completely filled with the oil, it prevents the refrigerant vapor from flowing up the large risers and diverts all the refrigerant up the small risers. So especially for the small capacity, what will happen? So the oil drops into this particular line, and it fills the oil trap in this case, because for the minimum capacity, the oil velocity is not sufficient to take up this oil or to carry this oil through these risers, and so the oil drops here and collect in the oil trap. And after some time, this oil trap is completely filled with the oil, and so it blocked the flow through the large risers, and the maximum flows takes place through the small risers. As this is a smaller diameter, the velocity is still adequate, or it is greater than the uh, larger riser. So the refrigerant is made to flow through these smaller risers. But at the same time, inverted trap is provided at the larger riser, because if it is connected, generally happens that some oil may drain back to the large risers. So to avoid that, the inverted trap is also provided for the larger riser. So this way, the arrangement is provided, especially if the load variation is high, and if for extremely low load, this comes in functions, and this prevents the blockage of refrigerant entering into the compressor. So in that case, the maximum refrigerant flows through the smaller risers. If the capacity again increases, then whatever, because of the high velocity, whatever the oil, the higher velocity clears the trap oil, and the refrigerant vapor again flows through risers. So in that case, that trap is clear because of the high velocity of the refrigerant. So here, it is not necessary to use the oil return line, because if the capacity increases, definitely that oil clears up and goes with that high velocity vapor entering into the compressor. But in single riser case, there is a possibility of these things. Some return line is required because to drain this oil. So this is about the double riser. So there are two possible arrangement of suction line: single riser and double risers. So single risers are generally recommended if the capacity variation is not too large. Means if the capacity variation is hardly 50% to 100% variation. But if the capacity variation further increase, that is maybe its variation span is more, suppose for 10% to 100%. In that case, it is recommended to have this double riser for suction line. Discharge line, it is called a hot gas. So the design and sizing of discharge lines are similar to that of suction line, because both are the gas lines. Similar to the suction line, the oil return and optimum pressure drop are the primary considerations in the discharge line. In the discharge line, oil doesn't mix with gaseous refrigerant. Generally, that oil is in the form of mist. So that's why some oil separator which trap that mist is provided. So that care is taken. It is entrant in the gaseous refrigerant at the discharge outlet of the compressor as oil mist. This piping line must be able to withstand the discharge pressure and temperature, because the maximum pressure is there in the discharge line, and also the temperature is also maximum. So whatever the piping provided, it must withstand that pressure and temperature as well. The allowable pressure loss in the discharge line, so that is hardly 10 to uh, 10 to 20 centimeter of the Hg. Then the recommended velocity is 300 to 500 meter per minute. This is the recommended velocity in the discharge line. The friction in the line increases power requirement of the compressor. So because that's why the velocity recommended and pressure loss recommended are there. So while designing, these two factors must be taken into account. So pressure should not exceed about 10 to 20 centimeter of Hg, and the velocity should not exceed 300 to 500 meter per minute. About the liquid line, to carry liquid refrigerant from the receiver to the expansion hole, that is the main rule of liquid line. Friction loss has no considerable effect on capacity and power, because here in the liquid line, the friction loss is not that much considerable. So not that much considerable factor, but the friction losses causes the evaporation of refrigerant. If there is excessive friction happens in the liquid line, there is a possibility of evaporation of the refrigerant, which is not desirable because it reduces the mass flow rate through the expansion wall. So that it should not be too high because it mainly causes the evaporation due to drop in pressure. The allowable pressure loss here is a little bit stringent. That is 1 centimeter of Hg per meter of length is allowable pressure drop. And so these are the four factors. So at the end of this particular topic, you should illustrate what are the consideration during pipe selection, what are the design considerations of refrigerant piping, then how to determine the sizing of the copper piping. Then you should be able to explain the design considerations of suction line, discharge line, and liquid line. So with this, this topic is completed. Next topic will focus on the capacity controls of reciprocating and centrifugal compressors. Thank you very much.